I think we study much about the fluid equation or some dispersive equation which comes from the fluids. So I think I have to study, explain more about the kinetic regime because it's totally different regime. So I think there are several the early career of graduate students. So I think this whole story may be fun to you. The kinetic regime or fluid equation are all a part of whole interacting particle systems. So there are three different ways of describing interacting particle systems. The first method is microscopy regime. In microscopy regime, we assume n balls. Ball number 1, ball number 2. And we assume perfect elastic collision between all these n balls. And just Newtonian mechanics govern everything. But of course, as you know, n is large. It's nearly impossible to describe the position and velocity of each particle at some time t and its location. So as asymptotics in terms about n, the second way is to Microscopy regime. We imagine we have infinitely many number of balls. Instead, we assume that we cannot specify the velocity of a particle at time t and location x. That means for time t and x, we just describe the dynamics of particles in terms of probability density function, say capital F. So in this regime, I will explain there are many equations, say the Boltzmann equation, what I talked to you today. And some different version of Landau equations or BGK equations, and so on. The third way is what we studied today many times. Microscopy regime. So this is deterministic. The second guy, the microscopy regime, is probabilistic. And the third guy is deterministic. So this is not probabilistic. So we imagine, we think that we can specify the velocity of particle at time t and x. So in this regime, we saw many equations are Euler or Navier-Stokes. The one thing interesting is that the three kinds of different description is not distinct. That means if we have microscopic, mesoscopic, and macroscopic. How can we relate the three different regimes? So in this ball, we imagine the radius of each ball as size epsilon. And mathematicians guess, and they're trying to show that if epsilon goes to 0 with some scaling for volume, with some scaling, and then they invented so-called Boltzmann gradient limit. And partially they succeed. They show that in this microscopy regime, they showed they can derive the Boltzmann equation. And also we can show that can derive Euler or Navier-Stokes starting from microscopic, say, the Boltzmann equation. Then which parameter do we have to show to infinity or 0? In the Boltzmann equation, there are some factor which is called Knudsen number Kn. The physical meaning of Knudsen number is mean free path. That means if you assume the first collision and then second collision, the distance, the scaling of this distance is called Knudsen number. To send macroscopic to microscopic, we make the system dense. That means we should send Knudsen number Kn to 0. And then we will derive Euler or Navier-Stokes by so-called hydrodynamic limit. I want to explain more about hydrodynamic limit, but Professor Ju-Hee Zhang is an expert, so I will close my mouth now. So what I want to say is today my research interest is about the Boltzmann equation. So macroscopic equations, Euler or Navier-Stokes, describe fluid. By microscopic, the Boltzmann equation or Landau describes the rarefied gas. Then how do we describe, how do we write the Boltzmann equation? The Boltzmann, or Boltzmann equation. The Boltzmann equation is imposed by the two famous physicists, Boltzmann and Maxwell. And it's PDE of probability density function capital F at T, X, V. Of course, we usually assume three-dimensional space and width also in R3. So this is combination of free transport and collision operator. The Boltzmann equation is written by the left-hand side is free transport. And right-hand side, Q, F, and F is quadratic nonlinear. Collision operator. The one thing different to fluid regime is that when you think about the Euler equations, this is nonlinear itself, right? But this is linear because V is not a function, V is variable. Right? So before we study about something tricky, quadratic nonlinear collision operator, I'll explain the meaning, the very simple meaning of free transport. Let's think about the particle at time t, x with velocity v. Then let's imagine it's backward in time trajectory and time s. We write location as capital X at time s, where this particle was at phase space txv. We also think about the velocity at time s at capital Xs as capital V t. If there's no external force, it's really easy to construct Hamiltonian. by simple Newton mechanics. And also we have no external force. So we can easily derive the left-hand side, if nothing, but the rate of change of probability density function at Tx with velocity v. That means d over ds, s as rotation with the velocity measured at s equal to t. This is so this guy. So this is very easy to understand, but what is quadratic nonlinear collision operator? This is very tricky. So first, let me write the form of quadratic nonlinear operator. The Q, say F1 and F2, is integral operator for U equal to R3 and omega in S2 with at Txv. U minus v minus u, also function of omega. This is collision corner. Times. As I told you, this is quadratic nonlinear, so it is written by the product of f1 and f2. f1 and u prime. I'll explain what u prime is. F2 v prime, of course, those are measured at time t and location x, minus f1 u, which is integral vector, and f2 v. It's the u, the omega. This is Boltzmann equation. What is u prime, v prime? In kinetic theory, in microscopy regime, we assume perfect elastic collision with two particles. We never assume the collision of three particles. Also, two particles with same mass, with u and v, and after perfect elastic collision, we have u prime and v prime. The first thing we have to do is that expressing u prime v prime in terms of u and v. So perfect elastic collision implies the four conservation. The three comes from momentum and one comes from energy. It means u prime plus v prime is u plus v. It contains three scalar conservations. And energy conservation. So from this four conservation and u prime 6 prime, which requires 6 scalar, we can understand why we need free variable S2. Because to express u prime v prime, which contains 6 scalar, but if we have only 4 conservation, we need 2 free variables. This is the role of such free variable, S2. Okay, now let me talk about collision corner B. The B is written by the velocity to the gamma times some nice function Q0 times zeta, where where gamma is between 0 and 1, it is called hot potential. And gamma equal to 1, we say that this collision model is hot sphere. If gamma is inverse low, we say that it is soft potential. So simply speaking, this is hard. So I don't know how to do that. How about Q of theta? Theta is cosine. Theta is u minus v with omega. So this form of intercorner is called cutoff intercorner. This form is called cutoff model, or sometimes it's called the grass cutoff. What we call this guy as cutoff. So original model has singularity in this guy. The quantity B has singularity. So simply speaking, this is not L1. So this singularity comes from when these two particles are grazing. So people arbitrarily cut those singularity, because even though we cut the singularity with the function, say, some cosine, it is still very good. Oh, I'm sorry. The Q of theta is bounded by cosine theta. So we cut the singular function with somehow some good cosine function, but still it is good. Let me explain more about this Q operator. Since our corner B is L1, we can split the operator with the prime stuffs and non-prime stuffs. So this is called Q gain. And gain and non-prime is called Q loss. This is possible because we assume that B is L1 through cutoff. Why we say this is gain and loss? Think about. We have uv, u prime, v prime. Our function is in terms of v. If we have u prime, v prime, that means it comes from some function v, right? So that means if we have u prime, v prime, it's more some positive probability we had v before collision. But what if we have v? If we have v after collision, we will lose a particle with v. That's why we say the second part as Q loss. The next part is, as far as I know, is kind of model. It's called the short range interaction. For short range interaction, there are many models which consider Coulomb force. And as far as I know, this hard sphere is just the fundamental with no Coulomb force, without any force. And depending on the type of Coulomb force, I know that the power may vary. The next important notion of kinetic theory is equilibrium state. Since each particles collide together, from statistical physics, many physicists expect that this state will converge to some equilibrium state. Or mathematically, it's just steady solution. And in kinetic theory, it's called Maxwellian. Let's try to find steady solution, which is time independent, to our Boltzmann equation. And the most basic form, and what you have learned so far, is that the function of V only, which has Gaussian. If you think about this Gaussian, it's super easy that free transport gives nothing because it contains only differentiability of t and x. How about the right-hand side? On the right-hand side, it's also easy from the nonlinear quadratic operator and Gaussian. And then F1, F2, at prime it gives this is what you see in integral. But we know that energy conservation, and this gives 0. So in statistical physics and kinetic theory, for the Boltzmann equation, our aim is clear. What is asymptotic state of Cauchy theory? This is what we want to show. In fact, from the several decades ago, there are many results about this result. But today what I want to talk is about the boundary problem. How do you impose? What kind of boundary problem do you have to impose on the boundary? So let me think about a simple domain. Since we are in the phase space, Txv, in trace sense, if you need, at time t, we're particle on the boundary, and there are many possibilities of velocity to the inside or to the outside. And I think about f as information which propagate with direction of v. Then what I have to show is that on the boundary, what I recommend for this guy is that think about you are the boundary, and you observe all the information from the inside and cook up the data and get into the boundary again. The uninormal. To set up all this guy as gamma plus. And as gamma minus. And what is the information you get when you're on the boundary? It is gamma plus what you get on the boundary. So what you have to write is that the way of giving the information to the inside after cook up. That means f this is the direction to the inside, right? As a function of information what you obtain. Okay. There are many models. So many physicists, I met some physicists in Texas, ICS, and they are trying to make some modified version which is really, really same as physical experiment. But at least in mathematics, the four fundamental boundary conditions, two are very not interesting and two are interesting. The first one is inflow. Inflow boundary condition is nothing but the data we give to the inside is nothing to do with what we observe. That means just given. The second guy is bounce back. If we get the information from this direction, and then we just pay back the same data to the opposite direction, it somehow looks like the two particles is motivated by two particles which travel 2 points back and forth. Of course, this is not realistic. The third guy is diffuse reflection. Which is motivated by heat motor, is what you give to the inside is the first we combine all the data, all the normal flux. All the normal flux. And then we consider this amount. This is only function of t and x only. In terms of v, the boundary, but by heat motor, instantly boundary make this guy as equilibrium state, Gaussian, with some proper normalization constant. The last one is most fundamental and ideal model, which is billiard model, which is called specular reflection. And it's just billiard. So F is F Tx, where R is reflection operator. Let's think about trajectory for finite time. How many bound on the boundary do we have to consider to solve these problems? This is nothing. For this guy, we just need to consider only 2 bounds. For this guy, for diffuse reflection, the position observed data from all the direction, but this is not geometric. It gives to the inside with some Gaussian profile. It just say whole amount of information, right? So in boundary condition 3, we also have to we just consider only the first backward bounds. How about specular? For specular, we have to keep track the trajectory until time 0. Many bounces. So I will show you the key idea of showing the answer for this question for about boundary condition 4. So this question was introduced by Shizuta and Asano. And 4 decades ago, and partial result, say good result, given by Yan Go, 2010 for all these 4 boundary conditions, but for spectral reflection, but for 4th boundary condition, he had to assume that the convex boundary is analytic. Except this spectral reflection boundary condition, he showed that it's possible or smooth convex domain. And then this was boundary condition 4 for general C3 domain was showed that by Kim, and I did it. And we showed that for external force, when external force is time dependent, and second case is time independent. Let me briefly explain the difference between time dependence and time independence. If the external force is time dependent, then final energy is unknown. So it is nearly impossible to specify the final state. We expect final state is mu, but it is true when mass and energy is conserved. What if we don't know the final energy? We can't say nothing. Instead, if the potential is time independent, we have energy conservation. So we show that the state goes to mu exponentially in time. Let me briefly explain why this boundary problem was solved very recently.
Your result is what the solution
exists globally
in
and it's a weak solution.
Weak solution.
Yeah.
Yes.
Yes. Now I will say about the limit of differentiability of these boundary problems. So if you think about, say, whole space problem or torus, periodic boundary condition. And there are many results by Villani, Muho, Guo, or some the previous result, many results. And in the case of periodic boundary conditions, a torus, high order regularity solution is available. But in the case of boundary condition, boundary problem, it's known that the hard regularity is not that easy because on the boundary, let's try to decompose the direction as normal, v normal, and v tangential. And then we can transfer the operator v dot grad as v normal, v tangential dot normal derivative and tangential derivatives of f equal to f and f. And what do you see? Let's see this. Normal derivative of f is somehow looks like 1 over normal velocity times quadratic nonlinear operator. But as we see, in the form of quadratic nonlinear operator is non-local, right? Because it integrates all the possible area of velocity. So this is never zero. That means it's below up, as if we have very grazing velocity near the boundary. So because of this problem, what people introduced is to L to L infinity bootstrap. We will not say about regularity. We will assume that the initial data is in L infinity, and we will show that the solution goes to Maxwellian in just uniform sense without differentiability. If you write probability density function capital F as Maxwellian and its perturbation, our aim is to show this perturbation goes to 0 as time goes to infinity. And if we put this form to our Boltzmann equation, what we get is so these two terms come from linearized operator, which comes from the interaction between Maxwellian and perturbation. Say, Q of Maxwellian and perturbation and Maxwellian, because we know that it is quadratic nonlinear. So this is interaction between perturbation interaction. And of course, we will assume that the initial data F is very small, and this is really small. So it's technically it's well-developed area. So we will focus on this linearized Boltzmann operator. What is nu? Nu is very good. Nu is function of V, which is uniformly looks like Japanese bracket V gamma, but let's assume that hard sphere gamma equal to 1. And K is integral operator, which is compact operator L to L2. Say KFV is since capital K is compact, let's say this small k is very good. What I'm saying very good is it has very good decay. Good decay and very weak singularity. And first property of what gives nu is very uniformly exponential decay of f along the trajectory. So this implies we have d over ds e to the minus nu at vs s f 0 at xs vs at time t equal to 0. That implies, oh, it's plus. As s goes to infinity, we have exponential decay of the data. Oh, it's s. We have something on the right-hand side, kf, which may growth, but we will show that it's not that severe. The second thing is L to decay. If we consider L to energy estimate in terms of f, and then we will get because we have free transport, it's very easy to show. And usually, we'll see f of L2 here, but the nature of this linearized operator, we see this guy. We lose P. What is P? P is operator P is null space of linearized operator nu minus K. So to obtain exponential decay of L2, we have to recover the missing part PF. So what you have to do is we recover. That means we have to estimate the missing part from what you have. This is called coercivity estimate. If we have coercivity estimate, we will show that with this coercivity estimate, we will show that L of f goes to 0 exponentially. Then how we combine decay of L infinity and decay of L2? What do you know? Yeah, bounded convex, uniformly convex. Okay. Yeah, uniformly convex.
In the whole space.
For whole space, everything was solved by some higher regularity method.
But the estimate still works. This exponential decay.
This guy? No, in the case of this is kind of this is so-called confinement. So. To think about Navier-Stokes. If you have Navier-Stokes on the boundary, and if you assume a smooth solution, then we have right. But from if it is bounded equal to 0 by coercivity, this is bounded by something like this, and we know that U goes to 0 exponentially. This is what you know in the case of bounded domain. How about this guy? In the case of whole space, this is coercivity doesn't exist. To get coercivity, we have to fix some power. So this is called polynomial decay. Some functional space, but it may see 1 plus 1 over s like that. Then this K it looks like a plus 1 over t, like this. So it's easy to imagine. So if this is bounded, their interaction will be stronger. So we will get stronger decay to something. But if we have a whole space, then their information is not interacting with its neighbor, but it goes to away. So decay will be weaker, way weaker.
Okay, my question was mathematically that in the bounded domain, you can just use a Poincare type inequality.
Yeah, right. Yeah. Poincare type.
Here, it's not obviously there's no derivative, so we don't have a Poincare type.
Yeah. So for this guy, with this coercivity estimate, what you know just decay of f of L2, and I'll explain how we derive L infinity decay using L2 decay in the next page. Okay. I'll fix that. The idea is 200 principle. With some treasure. With TXV. As a TXV is bounded, is obtained by some kind of the sum of all this, the previous information on this trajectory. Say, if the px3 is written by some integer data and time integration of some decay, f of s, xs, 3s with some velocity assumption. But since k is good, let's say it's 1. With some velocity is uniform bounded. If you think this trajectory one more time, this time x, position xs, and velocity u, we say this integer data plus time, and velocity u. This is u and u prime. Say u prime. Integration u prime, both are bounded, say, because k is good. And f of s prime, xs prime, 3s prime. This is what you get from trajectory analysis with double dual trajectory. What you get is that if the information we have is exponential decay of f, we know that including x3, but we have double integration in two velocities. So we have to change one velocity integration to space integration. That implies we need non-degeneracy. That means when you start this guy and it's as prime, the determinant of dx and s prime over Jacobian. If this is uniformly positive, we can change u, and since it's bounded. And using some folder, we can show that. So the initial data and time, which is just uniformly a decay factor, and f of L2. There's a competition between the growth factor, but we still have decay factor, and we know that this is also decay, and this is a way of giving this. So this is called bootstrap, the controlling L infinity through L2. Okay, we show that supremum of x t f of L infinity with some weight say f. So this is the rough structure of argument. This is a way of avoid the requirement of differentiability, since we don't know how to treat in the case of bounded problems. And I will stop